Okay, we're going to look at an example of code and our algorithmic analysis for the complexity of an algorithm. So we have here a little piece of code that takes a list. In this case, the list is the 333 three times. And it's just going to loop through the list using the loop that we're familiar with, and it's going to print this out. Now, what I'm going to do is I want to find out the complexity of this code experimentally. So far we've been looking at the complexity of the code analytically by analyzing the code. So we say, okay, well, there's a for loop, and the for loop is going to execute x's length times. So that's linearly, this line of code is going to execute 3 times. In this case, if we add more values, if this is 4 times, then the code will execute, this line will execute 4 times. So here we are saying analytically we've decided that the complexity of this algorithm is O of n. It runs in time linear to linearly related to the input. So we would write O of n. But what if I didn't know how to read a for loop, and I still wanted to figure out this complexity for this? So we can figure this out analytically. So let's visualize this execution. And what we actually care about here is just the number of steps. So we're interested in how many steps does it take for this code to execute. So here it's 12 steps. So I'm going to start entering these values in my spreadsheet. So I'm going to say size of list. That's going to be n. And then I'll say number of computations, or number of steps anyway. So for size of the list is 3, we have 12 computations. Now let's go back and edit this code. Let's add in an extra line here. Now we have 15. So if our size of our list is 4, we have 15. I'm going to do the same thing. I'm going to add more value. Now the list of length is 18. 5 responds to 18. This code 5, 6. 6 is 21. I'll type in 6 and I'll type in 21. You could probably even guess what will happen now. But what we'll do is take this. We're going to generate a graph. So we have the number of computations versus the size of the list. And what we'll do is, it's not a line chart. We have a scatter point, right? Because we just have single points here, sample points. And what we want to do is come up with a line of best fit. So we're going to add a trend line in our Google Docs here of a linear fit. We'll show the r squared, which just means how well does this line fit. And if it equals 1, it means it's a perfect fit. So here we can see we have a perfect fit of a linear trend line. And this linear is the O of n that we were looking for. So here we're seeing experimentally the O of n complexity. Now let's go back and let's try this and see how it works for something else. So I'm going to add in an extra list. Now we're going to change this one to J. And it doesn't really matter what we print here. We just need this to work. So let's go back to 3. And we'll see how many times this code executes. So this will now take 42 steps for an input size of size 3. So I'm going to make a new sheet. I'm going to copy our headers here. Say for 3 we get 42. And then let's try this for a list of size 4. For a list of size 4, we now have 67 steps. 4 goes to 67. We'll edit this code. List of length 5. goes to 98. 5 goes to 98. 6 goes to 135. Be pretty good, but let's add in one more. Maybe we add in, skip a couple steps now. 7, 8, 9. So 9, a list of length 9 takes 282 steps. 9 takes 282 steps. Make a graph, this one. Okay, so here we have our list, and it's a little hard to see what the trend is here. So let's generate our line of best fit. Do the trend line. And right now we have a linear fit, as we can see here. And this linear fit, you can see there's a few dots that aren't quite in the right place. So let's show this r squared value. And we can see it's less than 1, which means it's not such a great fit. So I'm going to say, let's use a polynomial, and I'll use polynomial of degree 2, because we actually expect that this code is going to be O of n squared, because we have a nested loop here, right? So we're expecting to see the line of best fit when I use a polynomial of degree 2. Polynomial of degree 2 just means I have x squared. So it's a polynomial of line 2, and now our r squared value is 1. So we're getting this very nice fit here. So this is exactly what we expected. So what we can do is actually use determine these values experimentally, right? And so again, the actual formula for this is not going to be just x squared, right? Because 4 squared is not 4 squared is 16, not 67. And 5 squared is 25, not 98. But what we're seeing here is we don't care about the particulars of the values. We don't care about that exact formula. We just care about the dominant term in terms of cost. What determines the rate of change? What determines this slope? And here, it's really talking about what is the line of best fit that we would assign here. So if we had a algorithm that was 2 to the n, we might use the exponential. Or if we had an algorithm that was cubic, we would want a polynomial of degree 3. Right? So if we had an additional for loop, so that we were 3 times nested in our for loop, then our algorithm, and we ran the same computation, we would end up with data points that where the line of best fit would require a polynomial of degree 3, and that's how we would experimentally verify that the complexity of our code would be O of n cubed if we had 3 loops here. In this case, we just have 2 loops, 2 nested loops together, and those nested loops give us n squared. And when we had a single loop, we saw looping through our list, we saw that linear trend, which was our O of n complexity.